I'll be chairing the afternoon session. And so it's my pleasure to reintroduce Rafael Piestun, University of Colorado Boulder. So what we're going to do is combine the two lectures into just one 90-minute session, so we'll finish at 3:30. Okay, please, Rafael.
Okay. Can you see the screen?
Yeah.
Good. Okay, so this is a bit continuation of what we started last Tuesday. I'm going to talk about super resolution microscopy. The point here is this: who knows there is a resolution limit in optics? And we know that the resolution limit is ultimately determined by the wavelength of the light. So if I write here, okay, can you see this? Maybe from the back now. So the wrist, can you see from the back? You see it? Well, this is so the reason you might not be able to see is because of diffraction. Now, this is certainly bigger than the wavelength, so that's a resolution limit imposed by the numerical aperture of your eye, essentially. And if you go far enough, you won't be able to see this, but this is still bigger than the wavelength. Now, if you get closer and closer, like we do in microscopy, you can get to see smaller things, but at some point, which is about half the wavelength of light, you will not be able to distinguish things that are smaller than that. In 3 dimensions, it's even worse. So that limit has been overcome in the 80s on surfaces by using near field probes, essentially by looking very, very close, looking at what's called the evanescent waves. But that has some problems. One of them being that it's only for surface investigation. So lately there has been a new wave of methods that allow you to actually beat that limit. Okay. So I'm talking about going 10 times smaller than the wavelength. So I'm going to talk a bit about that and relate that to the topics we were covering yesterday about the point square function and shaping light. Remember, we started to shape light in 3 dimensions. And we're going to see how that can help in these methods of microscopy. Okay, so here I have topics: diffraction, limited imaging. I'm going to introduce this new method. And then I'm going to talk about this 3D super resolution using shaped point square functions. Okay, so this is what we were talking about. This diagram shows essentially a plane wave going through an aperture, and then you have diffraction. If you haven't been in an optics lab, you might have seen this if you live close to the sea, and the waves of the sea. If you have a port, you can see the waves like that diffract. So that's essentially what limits resolution. Another way of looking at this is if you have 2 small point sources, say 2 stars in the night, each one generate, if you look through the camera or your eye, you see a bigger spot. And if they become closer, the 2 stars, at some point, you cannot distinguish them. Now, this is where leads to what is called as a Rayleigh criterion. And it's tricky because in these images we don't have noise. Ultimately, our ability to separate these 2 objects depends on the noise, the background noise. So that is something that only comes in the new theories of resolution, not in the classical theories. So the numerical aperture, this is a lens, and you look at the angles that you can accept in the lens. So if the angle here is mu, the numerical aperture is n, which is the index of refraction of this medium, sine mu. And here it shows that this blur here, as you increase the numerical aperture, becomes sharper. So yesterday, Ivan and I think Paul also talked about this. The resolution if you plot these things and look at the width of the lobe, you can see that the resolution in the transverse depends on the wavelength divided by the numerical aperture. Okay, so in order to improve resolution, you can use a shorter wavelength, so you can use X-rays, for example. But there you have some problems because X-rays are normally absorbed by most objects, and they are expensive to generate, and they kill things. Okay, so if you are looking at anything alive, it's not good. We still go through airport security and get some X-ray dose every week. So it's not good. The other option is to use higher numerical aperture, so you buy bigger objective lenses, but there's a limit. Ultimately, this at most can be 1, and that's it. So what can you do? Well, that's where we can come up with a new method. Then in Z, if you want to distinguish, if these 2 point sources are one behind the other, and you want to separate them, things are also dependent on lambda. Now the index of refraction appears here, but in the denominator we have Na squared, so as you increase the numerical aperture, these things improve more because it's square. But still, at best, this is going to be about 400 nanometers for a microscope, and this 200 nanometers, that's about as much as you can do. There, you can improve a little bit with the confocal and other tricks, but those are very incremental changes. This shows, right, in 3D, this point source function, if you plot it in 3D, so a cross-section here looks like this, but this also shows how things change in the axial direction, so things expand, right? If you are out of focus, this blur is going to be bigger. Again, this is the same thing, okay? But another way of looking at this is in the Fourier domain. So we talked about Fourier transforms yesterday. So the Fourier response, and I mentioned this yesterday, is just the Fourier transform list. Okay? So if you want to get the response in frequency, you make a Fourier transform of this function, and you get something, and then take the modulo square, and you get something like that. And so this is what this means. This is called the modulation transfer function. So if you are looking at the grating, this is low frequency. You are around here. That means that your response is good, so you're going to essentially see the same grating. Now, if you have a higher frequency, you are down here. The contrast is going to be reduced, and so if you look at this, you see lower contrast. Okay? And if you look at very high frequencies, like this, you might lose the contrast altogether. Okay, so that's the meaning of modulation transfer function. Now this cutoff frequency, which is the highest frequency you can see, that means this rating with the highest or smaller period that you can see is given by this frequency here. Okay, and that is related to this because it's the Fourier transform, and then taking the modulo, and that is 2 Na over lambda. Okay, so the resolution, another way of looking at resolution is in the frequency domain, and it gives you the higher frequency. The numerical aperture that the lambda times 2 gives you the highest frequency you can distinguish. If you have higher frequencies than that, you see gray. Okay, you don't see anything. Mathematically, this is the equation. Okay, it's called the optical transfer function. It's a Fourier transform. And when you take the modulo, you get the MTF. Is this clear? This is very, ultimately it's very simple, but it's important.
Rafael,
Yeah.
so going from the grating to the image,
Yes.
you're just assuming the grating is essentially a mask. And
The
you're
grating-
projecting the image.
Yes. The rating is what you track, the object you're trying to see. and the image is what you see. Okay, and the decrease here is increasing contrast. Okay. Now, this is related to Crisante's talk yesterday. In computational imaging, we have some freedom to make things. And we are not going to use just a lens. Okay, so instead of using a lens, we take the freedom to use masks, gratings, holograms, play around with different unconventional optics. We can also use illumination, play with illumination. We can illuminate with the structure, change the illumination, the angles, the wavelengths, etc. Pulses. Then you have this object, and what you detect here in this paradigm of imaging, what you detect is not necessarily an image, not necessarily what the ultimate thing you want to see. And this is a bit more delicate, but let me explain. So what you get here, then you are going to process and recover in the computer. But what you get here is not necessarily a one-to-one correspondence between the object and the detector. Okay. Normally with your cell phone camera, or with a cell phone, you take a picture and you try to make a one-to-one correspondence with each point here and each point here, try to make a one-to-one correspondence. Here you can have a different transformation and then use the computer to reconstruct. That's what happens in tomography, for example. In some cases, you might not even want to get an image. You might want to detect something. Any cancer or an object or a defect. So that's why I'm saying here is you can get a final image or a measurement. Your final information could be just yes or no. And this equation, let's say, just think of it as a generic transformation of light. Okay? Who knows how many dimensions light has? Or how many dimensions do you think it has? Huh? How many? 1, 2, 3, 4. Which are?
Amplitudes in 3 dimensions in the face.
In the face. What about color? Any other guess? So, well, you can look here and have more than that, because these are, we talk about this coherence function. Okay? We talk about the concept of coherence. So if light is coherent, yes, you have 3, 4, 5, depending how you count. You have amplitude, which is, that's not the dimension. You have the field is going to be, depending on the position, in 3D space, and then you are going to have frequency or color. But if you have incoherent light, you need to consider this magnitude is called the degree of coherence. And the degree of coherence is essentially tells you how you can relate or correlate different points in space. Okay, so the degree of coherence, who knows what interference is? Most? Okay. So when you have 2 points and you try to make an interference experiment, if you can have interference, you say you have coherence. If you can't have interference, you don't have coherence. So then you need to correlate all the points in space. So you have the coordinates of each point, which is 3-dimensional, the coordinates of the other point, 3-dimensional, and then you have the frequency, so it's a 7-dimensional thing. Okay? So that's why I'm showing here this is called the power spectral density, which relates this coherence function, and this is a generic point spread function in multiple dimensions. So this is a kind of a teaser because nobody works with so many dimensions. But it tells you that there are more generic transformations you can do here. Ultimately, what we see is if we try to make an image here, it's a 2-dimensional. Okay, so if you have a 7-dimensional function and you get a 2-dimensional function, you're essentially making a projection, right? So you're getting part of the information, you're losing most of it. And what I'm saying here is, let's try to do another transformation and get different information. Okay, images not always are what we want. Okay? Of course, this is going to be a detector array. It's going to be a CCD, so it's going to look like a meaningless image. But the question is, what information you can get there. So the main point here is that by playing these tricks, you may be able to capture information that is not normally obtained with just the lens. And for example, super resolution is what we are talking today. You can do 3D imaging, create images with no defocus that are all in focus, and things like that. Okay, so this is a bit of a philosophy thing, but you're going to see later how this applies. So here we're talking about the diffraction limit. Okay, is that possible? Okay, so that's the first thing. So this is Mr. Abe, okay, and Lord Rayleigh. So these guys in the 19th century, the first theory of diffraction, and also there was a diffraction limit. Okay, essentially what I showed you before was done 150 years and then 10 years, again, different use of the same problem. So, as you see, they are not very happy. They don't think it's possible. And in fact, 150 years, people thought that were trying to do this big diffraction limit. So it's not an easy problem. And there were pretty smart people who worked on this problem. Okay, so what we are trying to do is the opposite of what I told you before. So this is design is reversed and much smaller. Okay, so we are trying to do this by a lot, not by 1%. Okay, so the first method was that actually worked was proposed by Stefan Hell from Germany, and the idea is to use a type of scanning microscope. So if I talk about the was it you that talk about confocal? Confocal microscope. So you have normally confocal, you scan a spot and then have a pinhole detector. So now this spot, the smaller spot you can generate, it depends on the wavelength. So how do you do that? Well, you need to play some trick. And all what we said before was using what is called linear optics. Okay? According to linear optics, you cannot beat the linear. But if we use nonlinear effects, that's the trick. Now, people understood that, but how to use it was the difficult part. So what he proposes to use this donut-shaped beam, okay, in a way that it subtracts the intensity from this one, and so you get only the green one in the center. Okay, so the idea is to use two beams, one in red, one more in the, sorry, one in green, one more in the red, and essentially the sum gives you the difference. Okay, and how it works. So this is illuminates the same. We're talking about fluorescence image. Okay, so when you excite in fluorescent, okay, here you have the blue excitation corresponds to this one, and you emit in a longer wavelength. Okay, so you illuminate around here 500, you get light more like green, yellow. Now all this light comes from the same fluorophores, from the same particles that are emitting the light. Okay, shown here. Okay. So if a particle is in some of these states, now if you can deplete, essentially take all the atoms that are emitting from here down here, then there's no more emission. Okay. And the way to do that is to use this ring here in the red, and then who knows what stimulated emission is? It's the effect that is used in lasers. Okay. So in stimulated emission, you come with a photon, and you get another photon of the same wavelength. Okay. Those are two laser courses. So you illuminate here with this photon, and you get all the photons coming from this band down, and they have the same wavelength. So you can see, you can filter out those with a color filter. Okay, so all these photons are more reddish, so you can eliminate those. And then in this ring you're out of the photons. Okay, so there's no more emission here, and you end up with a smaller spot. Okay, so that's the trick, and this is called stimulated emission depletion microscopy. So this generates stimulated emission, this ring, and depletes all the photons from that area. Okay, so this is pretty new. He proposed this in the 90s, but was demonstrated only in the 2000s, in the last decade. And only about this year, or last year, there was a commercially available microscope like this, but people complain it doesn't work. It's tough to make these things work. Okay, so we went from a spot size like this to spot size like this, and now you can get, by increasing the intensity of this ring, this can become very, very small. So these are images from that group. So you have here, what is this? These are biological samples, okay? When you use STEM, this is conformal, this is the STEM. Okay, so you can beat this essentially by 10 times smaller. You can see 10 times smaller features. This essentially explains the same thing. Okay, and more recently, there's been a number of other methods. Okay, in 2006, there were 3 papers which proposed similar methods. So here the trick is different. Here the trick is to, let's say these are molecules. These are molecules, fluorescent molecules, and you see they are packed. So if they are emitting light all at the same time, let's say you illuminate with the green light. Oh, okay, let's not go. If all of these emit at the same time, you're going to see a big blur. So the trick here is to bleach all of them. Okay, bleach means you make them emit so much that at the end there's no more photons. Okay. Now you don't see anything, so that's not good like that. So now for some particular fluorophores, you can reactivate these molecules. Okay, so you illuminate now with a 407 green light, and some of these molecules are going to become again active or emitting. And you do that, you can control that with the power of this beam. Okay, so if you have more power, you have more molecules. If you have less power, only a few. It's a probabilistic thing. So now I have 3 molecules, and that can emit. And when I look at the image, I see three blurs. Okay, my blurs are still big in this method. But now, because they are separated and isolated from each other, I can say, okay, this molecule is in the center of this blur, this molecule is in the center. So now I can localize each of these, and so I can tell you exactly where they are. So, but I only got 3 molecules. How do I continue? Well, I repeat the process, and all the molecules that are going to meet are always going to be different and random and sparse. That's the key. So you get different images that each corresponds to different molecules, so you can build an image point by point. Okay, so by taking many of these images. So point by point you build an image, and now this has super resolution. Okay, because each spot here is localized typically with a precision better than 20 nanometers, as opposed to 200 nanometers, which is the size of the spot. Okay, so this compared to what you get normally looks better, right? So this is really exciting. These are images from the first paper from Schwartz group in Harvard. So these are conventional images. These are microtubules in the cells. These are the stone images, which are much better detail. Still, these are very researchy type of images. It's very tough to get these results. These are know how to prepare the samples. Because again, the fluorescent particles to use are very specific. They need to be able to focus switch or photoactivate.
Rafael? So each image is a time slice. You're doing a pulse experiment.
Right, so this image was obtained after, say, 1,000 images, and each image had a few points.
And are you assuming during the time of the pulse that you have only one molecule that turns on? As opposed to several?
You need a few molecules, not one.
A few molecules, but a given molecule will not blink on and off during the time frame of the pulse, is that correct?
Well, you have time periods and they do blink, but you are assuming that yeah, in each position, because you have only have one molecule. There is a lot of details I mentioned. You need to make sure that the table doesn't move. 10 nanometers, if you breathe around, it's going to change the index of air. So you need to have some way of tracking that things don't move. And in fact, things move and then you correct for it. So the first images took hours. Now they can take minutes, but that's still challenging in terms of the time it takes. One of the goals is to do this faster to live cell image. Okay, there is another trick. This is based on structural illumination. Who knows what the Moire or Moire effect is? Who has seen these images like this? Maybe you have a curtain or some periodic structure. So when you have a periodic structure like this, if you overlap these two, you get something like that. So what's going on is essentially down modulating the high frequencies. So the trick here is to eliminate the periodic structure like this. And this more effect, what does is, you see, you have high frequency, this is the rating. When you overlap these two, you see the same details here, but at lower frequency. Okay? You see lower frequencies. Okay? Lower frequencies. So by putting a grating, you bring down the frequencies. Okay? It's similar to heterodyning and homodining for those in communication. Okay, so you illuminate with this grating, and what happens is you generate essentially the frequency. This is the frequency domain. So the frequencies that are here are brought down to the zero frequency and so on. So essentially you are increasing your cutoff frequency with this method. And if you use a non-linear effect, you know that if you have a linear system and you come with frequency omega, you cannot generate other frequencies. Everybody knows that. But if you have a non-linear system, frequency omega, you can generate frequencies 2 omega, or 3 omega, 4 omega. So that's what happened here. If it's a non-linear effect, you generate 1, 2, you can go higher frequencies. These are the harmonics, which repeats this information. So then what you need to do is rotate this grating, different orientations, and you gather a space in frequency domain that is much larger than the original cutoff. So with that, you can extend the cutoff and increase the resolution. Okay, so this was developed by Gustafsson, then at the University of San Francisco. So we saw 3 methods that in fluorescent microscopy that can achieve the super resolution. And they are essentially all based on the same principle. The principle is that you are using some non-linear effect, because we said linear optics is not going to make it. And in all of them, you are switching some property of the material. Okay? So in what some people call targeted switching, you either have a beam that depletes. So let's say A and B are molecules that are active and not active, or bleach. So here you have A is active and B is bleach. And then you scan that beam. So you are activating and bleaching molecules as you scan the spot. That's the first method step. In this structural illumination, you illuminate with a grating shown here. So where you have the bodies, let's say you have A active, in the other regions you have B, you have bleach. And so again, then you move this grating in different orientations and you are activating and bleaching molecules. And in the other method, which is the palm and storm, palm, I didn't mention this, is photoactivated light microscopy, storm is stochastic, optical diffraction and microscopy. You have this switching on and off occurs at random. Okay, it's a probabilistic thing, so you have one active molecule and here, and most are dark. Okay, so they all are based in switching on and off the molecules. And how you do it is what gives you different methods. Now this one has, these are essentially scanning methods. This one is a wide field, so you see everything at once, but you need to wait a little bit of time. But there is another reason why this could be better, and that is because each molecule, it's enough that each molecule emits only once. Okay? Here, you actually see a molecule, that's what you need. Here, because you are scanning and these beams, every molecule is activated more than once, and that for some reason might not be good because you are putting more light into the sample. So in some biological samples, that's not good. You need more power also. Okay, questions about this? You got the idea, I hope. Okay, there is still another way of doing things. This is using quantum dots. Okay, quantum dots is another type of emitter. Okay, these are semiconductors. So the idea here is that you want to have these emitters and you want to, again, resolve, separate them. So here you have two emitters that are close together. And if you look at them, if you take an image, you can't separate. But if you look at them over time, okay, for each pixel of the image, you're going to get a signal. Okay? Each pixel, so this represents one pixel, another pixel, another pixel. All the signals are going to be different. So the signals that correspond to one quantum dot are going to be different than the signals for the other quantum dot. And the signals where you have overlap, they're going to be a mixture of course. So by looking at the time sequence and looking at the statistics of these signals, it's possible also to separate these two spots. This is work done in UCLA. So here you have the original image. You can't separate the spots. Now if you take second order correlations, fourth order correlations, you can separate the two sources. And here you have images regular and using this method. This method is not as good in terms of the resolution you can achieve, but it's very simple. And another method that has just been used for 2 point sources, not even an object, is using this method called independent component analysis, which is if you're in a cocktail party. If you're in a party, there's a lot of noise. You still talk to somebody and you can understand what the person is telling you, right? But it's still surprising that you can understand because there's a lot of noise, right? So how does that happen? Well, the brain is trained, but you can do something like that with the computer. Okay? And so you can separate signals that are together. Okay? This is also used mostly in defense applications. Okay? If you have signals coming from different locations and you want to know which one comes from where, you can do this processing and separate signals. So here it shows that you can separate two quantum dots, okay, even though they are very close. Okay? Even if they are overlapping, I think at this statistic. Now the problem with this is you need a lot of light because you need to iterate over multiple images and you need to measure these statistical properties. But this is directions that are interesting to follow because they could lead to other methods. Okay, so so far I haven't talked about 3D, right? what happens in 3D? All the images we see were 2D. So now I'm going to talk about 3D. So let's borrow from what we know about the eye. If you look at the one way, or the visual system is looking at the context. So how do we know this guy is closer than this one?
It's moving faster.
Yeah, it's blurring the image, and it's also bigger, right? Right. So the brain can understand those things, but those are tricky. And maybe this car is closer. It's just it's a small car, right? So you can trick the eye, right? Or maybe this is moving fast. This is closer, but it's standing, and it's a smaller, much better. So you don't know. So these are computer vision algorithms to use this key. Now the other one is parallax. Okay, you have two eyes that works. Now the problem with microscopy with the two eyes is that you don't have space in a microscope for two eyes. The only way, right? Because the objective is taking almost all the half space. So you can go to the other side, and that's cumbersome. Or you can cut the field of view, but then you reduce the numerical aperture. So this is not so good, although it's used in microscopy, but not for high-NA microscopy. So the other that is left is focus and defocus, right? So that works. Now we have, you just take a lens and focus in different planes. People use that. Chris and the President talked about that yesterday. But this is not. Well, the question is this lens the best way of doing this operation? Okay. So if you want to distinguish distances in Z, is a regular lens the best way of doing it? So it turns out it's not. Okay, so you can make a better lens. In fact, it's going to be a bad lens, but which is better for this task. Okay, these are along the lines I was telling you earlier. If your goal is to see something, use a lens. But if your goal is to measure the distance of something in depth, you might use something else. So here are a few solutions to that. Essentially what we're trying to do is locate a particle in Z. So one way is to put a cylindrical lens. So when you go to one side of focus, you see like a line horizontal. When you go to the other side, you see like a line vertical. So what's going on here is when this point source moves back and forth, you see these images. Another method is to use two images. Okay, one focused in one plane and one focused in another plane. So you have two images. One is in focus, one is out of focus. Now, if you move to a different location, they switch. Okay? Now, this one is in focus. You need to look two at a time. So here is in focus, out of focus. So taking two images can also work, but you need another camera. And then if you have a lot of objects, you need to find the correspondence. That might be difficult. And the other method is what I'm going to talk in a moment, which is using a bad lens that instead of giving you one spot like this, gives you two spots, and the two spots rotate as the particle moves back and forth. Okay? So instead of seeing one spot, you see two, and if the particle moves back and forth, these two rotate. If you make a 3D plot, it's like a helix, a double helix. Okay, so this is a bit more general than resolution. It's about localization of the particles. It's been used before these super resolution microscopies to measure forces in biophysics, tracking particles, and flow. You measure the flow in fluids, right? You have a lot of particles, you look at the position of particles. So it has application in biology, in physics, chemistry, for nanofabrication also. So it's a bit more general. So now I want to take you to the design or how we explain these things. And yesterday I talked a little bit about that. So we talked about this yesterday, about designing a 3D distribution. And you can look at this as once you have a model for the optics, it's a constraint optimization. Okay, so we try to find this length. I didn't talk about this yesterday. So one way of looking, you have your hologram or your band lens here, and you want to select a region where you focus, where you are going to generate these patterns. So the first thing you need to do is, because you do this in a computer, you need to sample, right? In a computer, everything is sample, discrete. So that's a key. Then you need to impose wave equation constraints. Okay, impose that this is a wave. And then remember that example I gave you. Let me see. Let's see now if I have it here. That we have light coming on and off. In some cases, these things are what you impose is impossible or difficult, so you need to put some hierarchy. Essentially, decide which aspect of these things that you want to generate are more important. And then use some optimization algorithm. One type of algorithm is what is called projection onto the constraints. And this is when you don't know how to do things, you just do it. And normally it works. It's like this. You say, well, I want something some condition to be satisfied. You say, okay, I'm imposing this. And then you impose the next condition, and the next condition, and you iterate. Okay? And eventually those things converge in some circumstances. Okay? You need to be careful because it could be like cutting the legs of the table. Okay, you never get there because you get one leg, you get the next one, and then you never make it. So in some cases, it's better to cut the legs all at the same time. Okay, do it in parallel. Okay, so do it in parallel. So you say I impose. You come with a ruler, measure the 4 legs, and cut them all at the same time. That normally works better. Now, what is this projection? This projection is imposed. It's essentially a mathematical word, but it's telling you a condition. So, for example, a condition could be we want to have light in some point in space. Another condition could be I want to have no light in another point of space. Another condition would be I want this hologram to be phase only, or essentially fully transparent, and so on. And this is a mathematical way of optimizing that problem. So one example, different from the one I showed you, is here. So we have these donut molds that are useful, for example, for super resolution. And as you go out of focus, the intensity goes down, and this angle here, the notch, is essentially expanding. So you like to have more constant as this speed propagates. So if you do this optimization, you can get something like this. Now this happens only on a certain region of space. Looks better than this one because it's more constant. Now we're going to see, oh, it's not another picture, but you get to this by losing the circular symmetry. You need to give up something. Now, if you are not solved for circular symmetry, if you are ready to accept a different shape of this donut with the side lobes, this could be the better solution. There are other methods I'm going to skip for the sake of simplicity today. There's another way of doing these things is decomposing in model solutions. So yesterday we talked about this being a Gaussian beam. Who knows that there are higher order Gaussian beams? Yeah, okay. Model one. So these are you have a higher order Gaussian beams. If you have all these Gaussian beams, you can generate any beam. So then you say, okay, well now my problem is I have this represents the Gaussian beams, and the only thing you need to find is the coefficients of each of them. Okay. And there are there are many. There are at least 2 ways of decomposing these Gaussian beams. If you use Cartesian coordinates, you get the Hermite Gaussian beams. If you use polar coordinates, you get the Laguerre Gaussian beams. Okay. So some look like squares, the others look like donut holes, rings. We're going to see those in a moment. So one thing we want to do is find this propagation invariant wavefields. Okay? And we're going to see in a moment soon why they are important. But the idea is to have waves that, as I say, despite diffraction, they have some invariance. So in this case, what I'm looking for is a wave with a smiley face, and after some distance, you get the same intensity, but a different orientation. So something that rotates, but still gives you the same image. In between, there's no lenses, there's only diffraction. So in order to do that, we use this Gaussian basis. So this is a 0, 0, which looks like this. And then as you increase n, the contrast is not good here, but you get rings. Okay? The higher n, the n number, you have more rings. And then m gives you the donut. Now the higher m, I don't have, because this is infinite basis, infinite set of functions. The higher m, this hole is bigger. Okay? And it's bigger because the phase has multiple jumps around the center. Okay, so this is a set of functions that, if you combine them, you can build anything. Okay? So you can plot them in a plot like this. M is this number, n is the other number, and so each pole is one dot. And to represent any beam, you need to find the coefficients, which here are marked in red. For any beam, you have a different set of coefficients. And it's a graphical representation of any beam. Okay? In terms of the Gaussian balls, for those that, before we talk about Fourier domain, so in the Fourier domain we represent things with sinusoids, here we represent things with Gaussian functions. This is an example of what you can do. So this is a beam that expands like a Gaussian, but on different planes you get a cross. Okay? This is real. Okay? So in the middle you have diffraction. And look at the diffracts, and then you get back the cross. And then diffracts again, and you get back the cross. Okay? There is something, a real laser beam. So you can do this thing. So we know we can do it. How you do it? Well, you go to this plane, and the trick is to choose modes that are on parallel lines. Okay, so if you choose dots on these parallel lines, you get something like what I showed you. You get something that is self-image with rotation. And the angle of rotation depends on the slope of these lines. If the line is steep, you get faster rotation. If the line is horizontal, you get no rotation. So these are special cases. One interesting case is a set of eigen Fourier functions. Essentially functions whose Fourier transform is the same function. So we know one, which is the Gaussian, right? The Fourier transform of the Gaussian is the Gaussian. Can you tell another function whose Fourier transform is the same? We had it before. All the Laguerre Gaussian and all the Hermite Gaussian are self-Fourier transforms. But also the comb of deltas. Who knows the comb of delta? Who knows the delta function? Everybody knows what the delta function is. So you have a comb of deltas. The Fourier transform is also a comb of delta. Except that the delta is not a function. We have to talk about it for complaints. What was the Dumble effect? It's a special case. The Dumble effect, if you take a grating, illuminate a grating is something periodic, and then you look behind and you get periodic patterns behind the grating. Okay? With no lenses. You get the same grating again. Bezel beams, we talked a bit about that yesterday, are beams that have a cross-section looks like a Bezel function, J0. And in principle, they don't diffract, in quotes, because everything diffracts. just over some distance, it looks like it doesn't diffract. Okay, so these are the eigen Fourier functions that have our horizontal lines, and you can build any eigenfunction with this formula. So you take any function g, okay, you multiply by I to the n, I is the imaginary. You take the symmetric, right, minus g of minus x is the symmetric, multiply by I to the n. Take the Fourier transform, flipped, multiply by minus 1 to the n. This is probably minus I to the n. And then add all this, and you get a function that is, has this property. It's eigen Fourier transform. So this is interesting. Let's skip this one, it's more technical. This one is also. Okay, here I have a different. Also, the phase map is self-reduced, except for the quadratic phase. So as this rotates, you get rotation. The phase looks the same times a quadratic phase. Now, this rotating things, continuously rotating, is also a special case. So those cases are when you have all the modes on one line. So if you have only one line, you get beams that rotate like this. You take a different line and you get beams like that. Okay? So nothing is moving. This is a cross section. So if I had this hologram here, I would need to move a screen to see this pattern. But it's like moving the screen over time. You can make things that rotate in time, but then you need to combine different colors, like have a beating of frequencies. So this was a first experiment showing this rotation. And you have a lot of rotation close to the Rayleigh range, close to the waist of the beam. It's essentially linear, and then when you go to the far field, remember the far field things are essentially constant. So one thing that is important is we showed before that, well, you can see that in the Gaussian beam, in the Rayleigh range things are almost constant, because essentially the definition of the Rayleigh range. So if you use a Gaussian beam to measure depth, things are not changing in the Rayleigh range. But here you have the maximum rotation rate in the Rayleigh. So this is more sensitive to variations in depth. That's the trick. That's what we're going to use now. Now with self-generating beams, we are going to take that hologram that generates that beam. And okay, so this is the aperture, the lens, and looking at different planes. Without anything here, you see the defocus. So now I'm going to put here the hologram, and what I'm going to see is this rotation. Now I'm moving as I move the screen, as I was saying. So this is better for, this is 3D, the same thing. So this is better to find the location of things in Z, and essentially give you this quote-unquote axial super-resolution. Good. So how do we use this in imaging and microscopy? What we're going to do is build a mask, a hologram, put it in the Fourier plane, somewhere in between the lenses. And if the object, can you see this here? Almost, okay. So if the red object is back, so the angle here is like this. If you don't see it, believe me. If the object is forward, the angle is in the opposite direction. If it's in the middle, it's horizontal. So that's, by looking at the angle, you tell the position of the object. Now, if you have a defocus, back and forth, they look the same. Because of the circular symmetry. So with only one image, you can take information about the 3D. The center of this pattern gives you the x and y position, and the angle gives you the Z position, at least in our crude estimation. So here is one example of a 3D imaging. This is the microscopy, but not really super resolution. There's some super resolution in Z, but not in X and Y. So here, this is a coin, and this is a T of the word liberty, and this is the reconstruction by taking two images. In this case, we take a regular image and an image with the rotating PSF. With these two, in signal processing, you reconstruct the 3D. And here, this is Lincoln, which is using the Lincoln memorial. And these are the two images. So normally, the way to do this is you use a scanning method. You use a white light, for example, 12 kilometers tall, and you scan this thing point by point. But here, with the two images, you make the same. You have the same function, so it's faster. And it requires a lot of processing. Okay. So here is a block diagram. We take two images, combine, use some type of Wiener filter, which is a deconvolution or deep blurring method, and get the 3D plot. Here is how it works with more detail. So I have this is a target used for calibration things, like the airflow. So the regular image, the rotating image. So you see here, take it now. The image appears there, the double. If you look at the 4, appears twice. So you take these two images, and then from these two you recover the punch press function up here. And if I move the object back and forth, you're going to see that it rotates. Okay, as you move the object back and forth. And you can see it here with your naked eye that the objects are, the replicas are like this, so the PSF is like that. So that's how you get the depth information. Now for particles, you don't need two images because if they are smaller than the diffraction limit, you do it like this. So these are a sample where with a laser we made 4 spots in glass of different depths. So with a regular image, you see 1, 2, 3, 4. These 4 look the same. You cannot tell the location. If you look with a double helix, you see the orientation is different in all of them. So just by looking at the image, you can tell they are different. Z position. Everybody sees the angle here, right? Now I have a movie, so here's what you need to say, wow. Now here. Okay? Good. Now these are, in this movie I move the object back and forth. So again, you can localize things with some 10 nanometer or better. Now this localization problem is a matter of how many of signal to noise, or how much signal you have relative to the noise. It depends on how much laser power or emission you have. So given these numbers, a bit tricky. You need to tell how many photos you used for this, and what was the camera, things like that. But this is good. 8 nanometers is very small. So you can localize things in 3D. Now, if you take, how do you tell the precision, the absence of random errors in your measurement? How do you do that? You make that measurement multiple times and look at the variance. Okay? So that's what we do here. Measure 100 times, and this is the variance. This is the standard deviation. Okay, so I told you, but you don't need to believe me that what is better or not. So one way of looking at this is to use a metric, okay? A number that tells you, quantify how good things are for something. Now, in statistics and information theory, people use this metric which is called the Kramer's-Rao bound. So what this tells you is how good you can estimate a parameter. Okay. And ultimately, every time you make a measurement, that's what in statistics is called estimation. Okay? It's not that we are trying to guess. It's a rigorous method. So let's say you measure temperature with a mercury, you take a thermometer, and you measure temperature with the alcohol. Which one is better?
In what sense?
Right.
Yeah?
In what sense?
More sensitive. So the one that expands the most with temperature, right? You say the alcohol? Okay. So alcohol is better because for every change in temperature, you get a larger change in distance. You are measuring the distance, you are not measuring temperature, right? You're measuring the expansion of the column. So that's essentially what this is. Nothing more than that, just more complicated so you don't understand. The idea is, if you want to change to have a measure of the derivative, okay, of the thing you are actually measuring, which is the height of the column, relative to the parameter that you want to find, which is the temperature. Okay, so these are these derivatives here. Okay, and you want to do that. So the fact that you use the log, it's not so important. So that's what you do. Now, when you have an image, you don't have only one dimension, you have many pixels, so you need to sum over all the pixels in this case. If it's a different measurement where you use different parameters, it could be an integral or summations. And then the probabilities are here because of the noise. So if you know if you have a Gaussian, white Gaussian noise or Poisson noise statistics, then you can show that the probabilities are eliminated. But essentially, it's to take into account the different options for noise. So going back, what you're trying to do is measure how fast things change with the parameter you're measuring, and that's the Kramer's bound. Now, that if you calculate that, it gives you this variance that I gave you here. Okay. It doesn't matter how you calculate that. For this experiment, there is a minimum variance. Okay? That's because this is for this or this, it's going to change so much, and that absolute minimum or fundamental limit is given by the Kramer's bound. The variance that you can do. There is a trick that the estimation has to be unbiased. That's a technical thing. So what we do here is, for a given experimental conditions, types of noise and things, we calculate that variance, the CRB, as a function of Z for Z localization. Okay, so this is for a regular lens, and in blue here is for the double heating. So you see it's lower. So that's good. Lower variance is better because you can have less error. And then it's more constant, which is also good. It means you can do that measurement over a longer range. You see. Okay, if the particle is here or here, it gives you the same precision. And similar for X and Y. Now, this is for a saturate, if you can saturate the detector. In other words, if you have enough photons in the measure. If you have I don't have it here, if you have a Poisson, if you have a limited number of photons, it's still better, but not that much better. Okay, so now I give you a number to quantify the fact that I was saying that double helix is better. So you need to, that depends on the problem. You can, for every problem, you can build plots like this. This is the hologram that we use to implement the double helix. And this is showing the dark field. Ivan talked about dark field yesterday. You can also do dark field with the double helix. It's good to eliminate the background. Okay. You can also track fluorescent particles. So here we have fluorescent particles. There. And here you see the double helices moving. So regular double helix. Of course, because here you're splitting the light into two lobes, the intensity is going to be lower, but that's still not a problem. And then you can track the location of these particles as well. Okay, so this is these plots for the case of a photon limiter, when you have a limited number of photons. Because if you are looking at the material, the scattering from a material, you can always apply a stronger laser use for photons. But if you're looking at the fluorescent molecules, they bleach. They give you so many photons. So you are limited by the number of photons. This is compared with other methods. It's complicated. Let's skip that one. Okay, so we have this holograms that generate double hit. This is what happens if you change the color, because the fluorophores have a not monochromatic. They have a low spectrum. So this plot shows the rotation angle as a function of distance for 3 different wavelengths. So it shows that it's about 100 nanometer boundaries. So if you change a little bit the wavelength up to 50 nanometers, that hologram still works. Originally, we were implementing this with a spatial light modulator. Now we are using a fabricated face mask. So it's a piece of glass, a photoresist that has a surface relief on it. Okay, so now we go back to the super resolution. Now we have this isolated molecules emitting. And if we use our mask here, instead of getting 3 points, we get 6, but now we can turn the position in 3D. We repeat the same cycles here anytime, and we can do a 3D map of the locations of these fluorophores. And if you have enough density, you can build an image, a 3D image. This was the first experiment we did. It's a fluorescent molecules inside PMMA. These are the 2 molecules, they look standard and magnetic. And this shows the location of molecules inside, these are random locations, inside the PMMA. And we found an example where 2 were very close. They were separated 14 nanometers in X, 26 in Y, and 21 in Z. Okay, so we have very close, 1 order of magnitude closer than the diffraction limit, but we can tell they are different. So that's resolution. The other methods, I showed this one with the astigmatic. There's another method you can use, which is with 2 objectives, and then interfering the light from the 2 objectives. It works pretty nice, but it has a small range, and it's quite complicated. To start with, you need 3 of these cameras, which each one costs $35,000. And your sample needs to be in this very tight region. So it's good for a lab, but not good for a mass production. Okay, one other thing is because molecules have molecules are more like dipoles. So all our assumptions were wrong because molecules are not really point sources; they are dipoles. So all what I showed you was wrong, except that if these molecules are not fixed, if they are moving around, and they are in many cases, they are not fixed. So if you take a dipole and move it around randomly, it behaves like a point source. Now, if the dipole is fixed, then it's a dipole, and that's going to affect the pattern. So one way is to measure the different polarizations. So what this diagram here, let's look. Here is a microscope. This is the illumination with the laser. Here, the 2 lasers. Remember, we have one for activation, one for excitation. And then here we have a beam splitter, and we have 2 paths, one for each polarization. So one polarization goes through the spatial light modulator and to the camera, and the other polarization is the same. So we have 2 different paths to do the same, but now we use a wave plate to rotate the polarization. So this gives you more efficient use of the photons, and also gives you more information about the polarization states. And you can get images like this, one for the one polarization channel, one for the second channel, and this is XY, XZ, and YZ, and for the two channels. So you can get two 3D plots. And something we haven't done yet is to combine these two. That's not easy because you need to find the corresponding molecules. It's not an easy task. So each point here comes from a double helix, a double low spot, like that. Let's keep this one. Okay, so I told you that in order to localize these molecules, it's very simple geometry. You have two spots, you find the center, that's the XY location. You find the angle, and that's the, it gives you the Z location. Well, we can show that that's not the optimum estimator. That is not going to give you the fundamental limit given by the Kramer's bound. You could do better, in other words. And why you could do better? Because there is information in the lobes, in the siders, the energy around those two lobes. Okay? And the way to do that, the AE represents angle estimator, which is what we were talking, and MLE represents maximum likelihood estimator. So maximum likelihood is, Crisante talked about it yesterday, but it's essentially using all the information you have, which one is the most likely pattern or distance that corresponds to this molecule. Okay? It's a signal post-processing, but it requires that you have a calibration, you have a physical model of the points plus function. So here we have a molecule. These are typical numbers, 1,000, 1,500 photons per molecule that you get. For one molecule, if you use this estimator, we got 20, 20, 40 variance. So sigma standard deviation. If you use this method, you can get instead of 20, 15, instead of 29, to 40, 26. So this is, we can show that this essentially can get you to the best possible, to that limit of accuracy. Okay, so if you make a cloud here in 3D, you get a football that is smaller. It's more confined. This is another example. Again, you go from this to this. So these estimators are more complicated. It's more signal processing, but it's better. Let me think if I want to talk about this. Okay, when we do this calibration, I'm going to talk about this. What is the calibration? The calibration is once you have the system in place, you take images of the point source, okay, as you go through photos. And in principle, you want to have images every nanometer over a range of 2 microns. That gives you about 2,000 images. It's doable, but there's another way of doing things is to measure the pattern on a few places and then interpolate. Now, the way to interpolate is not splines or anything like that, because you know that the wave, that this is a wave. So in order to go from here to here, you have the equation we saw yesterday, it's the Fresnel diffraction. So you can propagate these things and find the intermediate place. The problem is that you don't have the phase, right? Because the camera only measures the intensity. So you have the intensity in 3 planes, and you want to find the intensity in between. So you use this method called phase retrieval. So if you have, instead of having the amplitude and phase in one plane, you have the amplitude in 2 planes. Essentially you have the same amount of information, but you need to find the intermediate planes, and you do that by some algorithms. iterate, and you can get the face. Okay? Once you have the face, it's easy to interpolate. So instead of taking 2,000 images, we take 20 or 10. Okay, this is a 3D of a set of molecules that are localized with this method. As you can see, we don't see structure here. That's because we don't have enough density on the fluorescence. So now we are working on getting higher density so we can actually see things, not only demonstrate it in principle. Okay, so we show that there are now methods to beat the diffraction limit. Where is the limit now? The limit is clearly not diffraction because it's not limited by diffraction. What do you think is the limit? Don't cheat. The limit is essentially it's how good you can localize things, and how you can localize things depends on this. The limit is given by this Kramer's-Rao bound, and that Kramer-Rao bound is a function of the number of photons. So this variance, if you have more photons, the variance goes down. If you have less photons, the variance goes up. Okay. So
What's the probability distribution you use for computing this kind of route?
So this is with the Piestun, because that's the only noise that you cannot eliminate. It's the one that depends on the photon arrival. Okay, and light is photons, and that it's something you can change. You can also include other parameters, background noise, things like that, but that is not. In this case, we want the fundamental. So the fundamental is the shot noise, and so given the number of photons, you can find the fundamental. Now, that's for localization, but that translates directly into resolution for this type of method. Okay. Now, let's say you have you can get down to say around 5 nanometers. Well, then, if you did that, if you have enough photons and you can get to that resolution, then there are other limits. Okay, because the molecules themselves might be bigger than 5 nanometers. Okay, so what is the meaning of saying that you have resolution 5 nanometers if the molecules are bigger than that? So there is also a interaction between the molecules. Okay, think of this: if you have, we would say they were like dipoles. If you put 2 antennas close by, they're going to interact, and so there are other problems when you get too close. Okay? So the size of the molecules, the interaction between the molecules, those are farther. So we are still limited by this, but soon we are going to be limited by these other problems. Okay, so to conclude this part, we show that super resolution is not impossible. Requires switching of some nonlinearity, okay? Switching some molecules, some property of the matter. And there are essentially 2 big categories: targeted switching, which includes stimulated emission depletion microscopy, and stochastic switching, which includes this PALM, photoactivated light microscopy, and stochastic optical reconstruction. Now, I show how you can do sensing using these double helix microscopes. You can do localization, tracking, dark field, and so on. But you can also use it for super resolution. And one philosophical thing is that you need to use a processing matched to the optics. Okay? So in this case, we designed the optics using some signal consideration. And then we use signal processing to reconstruct the image. So we use signal processing in the design and in the estimation later on. So we use it both ways. It's not that we take an image and then we do the processing. So we need to work together with the signal processing and the optics. Okay? And possibly with the detectors and the KEMS, because it also critical is the number of photos you can get from every point. So, but in terms of signal processing, we use things like constraint optimization, model decomposition, chronoval bounds, maximum likelihood, phase retrieval. All these are concepts of the signals. So I always ask my students to take courses in signals and communication, even though they are doing experiments in optics. And I have to thank them because they do most of the work. Sean Quinn, Prasanna Pavani, Vini Sharma do most of this work. Sam Tony, Sam Don, and the other students in the past. Oh, Anura is now working also on these topics. Of course, I want to thank the funding, collaborators and funding agencies, particularly NSF, which has been very generous. Thank you. Questions?
Start off with one, Rafael.
Yes.
So you have to have a physical mask for making the double helix.
Yes.
And do you run into sort of manufacturing limitations to get the precision on the mask?
We've done it. That's not a problem because you calibrate the system. So if there are deviations from the design, as much as they are not very dramatic, it still works because you calibrate the pattern, and then you use this phase retrieval to get the exact PSF. So let's say your PSF doesn't look like this, but it's going to look similar. It behaves essentially the same. It's very quite robust to this type of aberrations. That's not interesting.
And the follow-up is the double helix, the optimal illumination geometry.
Well, the double helix is not the illumination. The double helix is on the passive side of the microscope. The illumination is
Right.
now, is it optimal? No, depends. So the key is this. We find out that there is not, double helices is not lenses. There are different types of double helices. Things like this. You can make this shorter range so that you get a double helix at a shorter distance. You can make the lobes smaller or bigger. You have different parameters with the double helix. And you can play around those. And there are trade-offs. So for example, if you want to have smaller spots, you can do it, but it's going to have shorter range. If you want to have a faster rotation, you're going to have less efficiency. So all these parameters you can play around, and it's similar to the lens where you control the numerical aperture. There are trade-offs. Increase the numerical aperture, you have the resolution but lower field of view. Well, if you have higher magnification, you have lower field of view. And here is the same. You can control parameters, so it's a class of PSFs. Now, are there others? Well, things go like this. If you have one spot, you cannot do it, that's a regular PSF. The next thing is you have two, right? You could have three, but then you have to spread more than this. Having said that, we have designed a PSF that has only one helix instead of two. So you can think of it as only one of these two. And that could work as well in some situations. If you have some private information. So it depends on the problem, you can find the helical PSFs. So that's a good question.
Any more questions?
Okay. Thank you.